Fantastic. So here's the questions. Are there any particular ones that you guys want to go over? Surely not. Now wait, all of them we're gonna waste our time, but like, cause I mean, like number six is like super easy. Like the reason I showed y'all number six is because you're perfectly okay with subtracting liters from liters, and the answer is in liters. So if you add or subtract 2 units, the answer is also in the same unit. That's all. That's the only reason I did that. It's just simple subtraction. Yeah. What? Yeah, because it says what volume of gasoline remains in the tank. Yes, absolutely. That's fine too, and it's not gonna hurt my feelings. Yeah. Sure. Um. Okay. So you're talking about like down here. This guy. Okay. 3 through 10. Like all of these. Okay. Four should have been okay. So this one should have actually checked out. Um. Let's see. Did it not check out? Oh, let's check it then. I may have goofed up. Hang on. Um, oh, you're right. You're right. Never mind. This one should have been the fact that this is a two should make that look like a problem. So, um, yeah, this one does not check out. Never mind. That's a no. Um, so y'all want to do number three? Okay. So X is for displacement, right? So which means that displacement is in meters. So I'm just going to write down meters on the left side. V and T squared. Velocity is meters per second for our units, so I'm just going to write down the unit. I'm going to ignore everything else. The T squared is seconds, so I'm going to write seconds squared. Plus, ignoring the 1/2, the A is in meters per second squared, and the T is in seconds, which means I should get everything to cancel out and equal meters, and I don't think that's going to happen because this is meters per second. This is second squared over 1. So I can get rid of one of the units here, but I can't get rid of both. So this one can go away, but that leaves me with meter seconds up here. So this already doesn't work. The one on the other side, one of the seconds will cancel out on the top and bottom, but they don't all cancel out. So up here we're left with meter seconds, which I don't even know what is, plus meters per second. This does not work. That's a no bueno. So that is not a dimensionally accurate equation. Okay, it won't work in real life. No way. Yeah, x is displacement and it's measured in meters. Okay, this one is F equals ma. This is Newton's second law. That totally works. Force is measured in kilogram meters per second. And when you take your mass, oh, sorry, kilogram meters per second squared. And when you take your mass is in kilograms, and your acceleration is in meters per second squared. So that actually works out on both sides. So on the left side, you get kilogram meters per second squared. On the right side, you get kilogram meters per second squared. So that one is a okay. Foot pound, we use Newton meters, but a Newton meter is an actual thing. Okay, foot pound is an engineering word for torque. In physics, the word for torque is Newton meter. Okay. Okay. Hang on. Hang on. XY squared is the x squared with this one. Look at this expression right here. XY squared is the x squared. Negative Ghost Rider, right? The x is not squared because there is an implied multiplication between these two variables. Okay, so if it was like this, x, y squared, then that is equal to x squared, y squared. So how do I know whether or not this velocity would be squared or not? Is because this is v times t, but there's no parentheses there. So if there's no parentheses, then it's regular velocity times time squared. If the velocity was squared, it would look like this. It would look like parentheses vt squared. And that would be squared velocity, squared time. Okay. That's a good question. Anything else? Yeah, energy. I think that's one of the questions that the digital people had too, was like E, like what is E? We didn't even talk about that in the video. And I did not, I'm sorry. Yeah, E stands for energy, and energy is measured in um, kilogram meters squared per second squared. Because basically it's force times distance. So you're taking a force in newtons and you're multiplying it by a distance. We'll talk more about that later, but that's the unit that we're looking for. So that means that on the right side, it needs to equal kilogram meters squared over second squared. Let's try it out and let's see if it actually does. So this kilogram meter squared per second squared equals, on the other side, I'm ignoring the 1/2. It doesn't exist. The mass is in kilograms, and the velocity is in meters per second. So I have meters per second here. So is a kilogram meter squared per second squared the same thing as a kilogram meter per second? So this is a no bueno. Okay? They're lying to you. If you remember the formula for kinetic energy, it's 1/2 mv squared, which is where they got that formula from. Um, and then down there it says E equals max for number 9. That is mass times acceleration times distance. Because I think if it's spelled out max, I think a lot of people are like, wait, what does that even mean? That's mass times acceleration times distance. So the same thing happens down here for this E. The E is in kilogram meters squared per second squared. And on the other side, the mass is kilograms. The acceleration is meters per second squared. And the distance is meters. So I actually think that works because a meter times a meter is a meter squared, right? So that's kilogram meters squared per second squared. So I think that one works. It's the same thing on both sides. So energy is mass times acceleration times distance. Seems to at least be okay, at least dimensionally. Okay. Yeah, 10 has a square root, and I think square roots hurt people's brains a lot, so I think it's probably worth doing. Um, velocity on the left, so our units are going to equal to meters per second on the left side. On the right side, we're going to have the square root of F times X. So the unit for force is going to be kilogram meters per second squared times mass, right? So kilograms. No, 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 no. Sorry, sorry. That is wrong. It's Fx. What is X? Meters. Okay. Divided by M. There's the kilograms. I put it in the wrong spot. I'm sorry. It's on the bottom. So F is kilogram meters per second squared. That's the unit for force. X is the unit for distance. And then the kilograms is down on the bottom. So kilograms force. Oh, sorry. Kilogram meters per second squared. That whole thing is force. I can probably find another highlighter. Yeah, I can change the color. X. Is that actually showing up? Okay, just kidding. JK. Oh, there he went. There's X. That's meters. And then go with 80s pink. M. Oh god, I can't even see that. Is kilograms. M is mass in this case, so mass would be in kilograms. Change that back to regular yellow. So, simplify. What do y'all want to do first? Cry first and get that out, and then cancel. What are we canceling? Kilograms. Okay, that's the easiest one because I see a kilogram on top, bye-bye, and a kilogram on bottom, bye-bye. So I'm just going to rewrite it. That's going to be meters per second squared times meters divided by nothing. So I'll put 1. Sorry, that doesn't even need to be there. Divided by 1. Anything divided by 1 is itself. It's gone. Okay, next step. Okay, so it's going to be meters squared over seconds squared. What's the square root of meters squared? And what's the square root of seconds squared? So that comes out to be meters per second, which means, surprisingly enough, that one actually works. No, yeah, that was a little bundle of trauma right there is what that one was. Okay, so if you start mixing units and square roots, things get interesting quick. And that's one of the formulas for the velocity of a mass on a spring. So hopefully, we'll deal with that later. Just so you know, we're going to be doing all of these like one step at a time. So if you started seeing all these equations and you're like, oh my God, I have to memorize all of these at once. No, you definitely don't. And some of these equations are bogus anyway. This is just more of like a mathematical exercise to see whether or not the units are arcane or not. If you didn't know energy, that's perfectly fine. It's not that big of a deal. Okay. Any other questions on the other ones? Are we all okay? In that case, let's take a little time and let's talk about the big three parts of motion. And two of them I don't really have to talk about a whole lot because you kind of know what they are. But the acceleration, we're going to have to talk about a lot. So I think, oh, these are just individual problems. Let me go to kinematics. I'm going to go to position. Is he already crying? Oh, there we go. That's fine. Um, okay, so there are three, like if we're talking about motion in general, there are three parts to motion. Okay, one of them involves your position. The other one is your velocity, and the last one is your acceleration. These are all related to time. Every single one of these, like all three of these, so I'm going to put up here. So I'm going to put all are time dependent. It is very much so. Okay, because like your velocity is your change in position in relation to time, and your acceleration is your change in speed with relation to time. Because you can't be constantly accelerating in one direction, because if you are constantly accelerating in one direction, you're constantly speeding up in one direction. So if that happens, you would eventually just be going so fast that it would be crazy. You have to stop accelerating at some point, or at the very least, your accelerations have to be balanced to each other. Because like there is like the falling example, so where like when people fall out of like airplanes and stuff like that when they're parachuting, you eventually get to a point to where you just stop speeding up anymore, and that's not because gravity just decided to be like, nah, bro. It's because gravity is being gravity is pulling you down, but air is pushing you back up. So your accelerations are being balanced out, and it just comes out to be like a zero acceleration. You don't really move. Okay. So these are all related to time, and your position is the baseline. Okay. Your position is basically where you are. Or I don't want to say you. Let's just say an object, because this can be more than just you. This is not about just you. Where an object. Right, the universe doesn't revolve around you, so like we'll just say we're an object, okay? Where an object exists in space. Now, us in AP Physics, we're going to usually refer to a position either by uh, a straight line position, so either just an X position or an X and a Y position, okay? You can have a positive position and you can also have a negative position. So if there's any, like, if you go below ground, because normally if you're like standing on the ground, we normally consider that position in the Y direction to be zero. And if you go underground, that's usually a negative position. If you go above ground, that's usually a positive position. Zero zero would be like our everybody's agreed upon sea level 0 0 point. Okay, so if you go below sea level, those are usually considered negative altitudes, and if you go above sea level, those are positive altitudes. Um, or if you're just like, if you're not having to reference everybody and you're just referencing yourself, you can make any position where you're like on the ground your 0 point. Okay, you don't have to look up your sea level reference to find out exactly what your position is, because these things are relative. Okay, my 0 0 can be somebody else's 0 0, but they can't both be the same 0 0. Does that make sense? Uh oh, yeah. Like, what just happened? Okay, so like, here's what I'm trying to say. You have two people. Here's person one, and here's person two. What I'm trying to say is both of these can't be 0 0 at the same time, because if they're both 0 0, that would actually mean that they're both in the exact same spot. Okay, so that doesn't work, right? But it can work this way. If this person says that they're the origin, this person could be like 2 3, right? And likewise, if I just carbon copy my picture, this person can say they're 0 0, and this person can say they're -2, -3, and both of these are okay. I mean, these are real. I mean, but this is a real situation, right? Okay. I have to talk about it because this is like how we do things. So like the zero position can be changed, but they can't both be the same 0 0. Like if we all agree that my position is 0 0, nobody else can take that coordinate, okay? So once you establish it, it has to stay that way during the problem, okay? You can reestablish it between each and every problem, but don't you can't have both of them be the origin location. So that makes sense. Good. I hope I'm not talking. I hope I'm not talking crazy talk. Okay. Also, the position can be a vector. Ooh, I lied to you. I'm sorry. Not position. If you want to make it a vector, it has a new word. That word is called displacement. Okay, and here's what I mean. So, like, a displacement is a change in position. So, if you walk over to that person, you're going from 0 0 to 2 3, and the distance that you cover between it is the displacement between those two people. And in this case, since it's moving up, +2 and +3, this would be a positive vector, okay? If you started at 0 0 and you went down this way, you're going from 0 to -2, and you're going from 0 to -3, so that would be a negative displacement, okay? I know it's at a little bit of an angle, but it kind of goes with the whole right is positive and down and left is negative kind of thing that we talked about yesterday, okay? So we have to the right being positive, we have to the left being negative, we have +2, +3. So if we're talking about going from one place to another, we're going to use the word displacement. We're not really going to use the word position. And since this is physics and everything moves, you're going to hear the word displacement a lot, and you're not necessarily going to hear the word position. Okay, does that make sense? Okay, are we all right? Nobody's hurting yet? Okay. Velocity is basically defined as how fast you're moving. Right, right. I said you, right? Sorry, I'm sorry. So the velocity is how fast an object is moving. Object is moving. And that comes out to be displacement over time. Over time. This is the only time I'm going to write it this way. Every other time you're going to see it as d over t. D stands for displacement, or you could also see it as delta x over t. I try to avoid using the deltas because in AP physics or even in high school physics, it's usually not required. So most of the time, you're going to see me write it as d over t and not delta x over t. Although if you take a physics class in college or you see some stuffy college professor, they may actually use the term delta x. And if they do, just understand that that's what they're talking about. Okay? They're being fancy pants. They don't have to because you could literally just call it displacement instead. Technically, the delta x is more formal, so it does work. It works probably better than what I do, but this is just kind of just enough to be dangerous kind of thing. All right. So I think we talked about how yesterday that velocities can be positive or negative, and it all depends on which way you're going. So I don't necessarily think I have to rewrite that, um, but it is important to note that if we're talking about displacement over time, this automatically assumes, and this is a big assumption, this assumes that you are traveling at a constant speed. Okay, and that is a big assumption. This assumes that you are traveling at a constant speed and you are neither speeding up nor slowing down. This displacement over time is for coasting on the highway mode. So if you are moving at a constant speed, you can easily use this formula to find out your speed. Okay, or if you are like in the case of like a speed gun, so like the police officers whenever they try to find people speeding down the highway, they're not going to like take a stopwatch and find your displacement over time and then give you a ticket. They're going to take a little radar gun and they're going to point it at you and they're going to get like an instantaneous reading of your velocity. So there are two different types of velocities that I guess we really kind of need to talk about, and that's the average velocity and instantaneous velocity. Okay. An average is just a total displacement over the total time. And you can get an average velocity and it can include your speeding up and slowing down. It just basically tells you the velocity of your entire trip. Okay. So the average velocity would be average. I normally write it out as AVG, or if you want it written as a letter, I do V with a little bar over it. Okay, and that's just total displacement over the total time. And what I mean by that is, if you were to take a trip and you started right here and you went this way for a long time, but then you went a different direction, then moved up and then down and then all the way across and then back this way and then over here. And then during these points right here, you had to like speed up and slow down. Okay, hopefully you didn't like take corners at the exact same speed. But but what you would do is you would just take your total distance that you traveled and you would divide it by the total time that it took you, and it would give you your average velocity. The average velocity ignores acceleration. Okay, so the average velocity is a tool that we use to just talk about like how fast we went in general. So if you were to, I think Google Maps tells you your average speed at the end of a trip. It'll tell you like, hey, you roughly did this, and it took you this long to be able to do it. Right. Does it tell you not whether or not it was legal or not? Or does it just it shows the speed limit? Fair enough. Okay, for the instantaneous velocity, we're just going to write as v, um, and it's just a small little point in time. Okay, so it's what you're doing at an instant. So it's still going to be distance over time, but this time interval down here is really small. Okay, and that's exactly what the police officers use whenever they use the radar guns. Is they send out a radar pulse, and that beam of light hits your car and then bounces back, and they send another pulse, and the difference in the time that it took between those two, they can calculate your velocity from that. So the time pulse between that though is like a millionth of a second. It's really small. So they use an instantaneous velocity to find out like how fast you're going at that particular time. This one ignores acceleration too, because the time interval is so small that nobody cares. Okay, so we can use velocity either by looking at like a really, really big average, or just looking at your velocity where it is at a very specific moment in time. Both of these are ways to ignore acceleration and be okay with it. Okay, because normally if you think about it in real life, we accelerate and we decelerate like all the time. It's like when you're walking somewhere, you're going at a constant speed, but then you stop. You had to slow down, right? So like, and then you can also avoid things like this because these are also fun. Let's say that you, this won't hurt, I promise. So let's say that you um, start at point A and then you go to point B and you travel just a straight line distance, nice and easy. And on the way there, you go at 20 meters per second. And let's say that it takes you, I don't know, 2 hours to get there. Okay, we could find our distance, but that's not the point. And then you go back from B and you do it the exact same way. You go negative 20 meters per second, and then it takes you 2 hours because you're a robot or something, and it was like perfect both times. What would your average velocity be for the entire trip? Zero. So did you even move at all? What? It's fine. 72,000 meters is just 72 kilometers. And 20 meters per second is like 40 miles per hour. We're not walking, Chief. This is, if you can walk 40 miles per hour, I really want to see that because it's going to look real funny. Okay, so the average velocity is going to equal 0 for the average. So in this case, if we were to do a trip, an identical trip back and forth, the average velocity really doesn't help you out at all because if you calculate the average velocity, it just comes out to 0. Likewise, if you start at one position and you go at a constant speed in a circle, this is really terrible to tell the NASCAR people because if you start off and you're going, I don't know, just pick the same thing, 20 meters per second, and you go around in a circle. What's your average velocity? It's 0. Okay? Because at every, and this is like for people who enjoy racing cars, this is a terrible point conversation to bring up because they don't like to hear that their average velocity is 0. Okay? But it actually is because for every point on a circle, there is an opposite location to it. So if you're moving down here at 20 meters per second, you are also moving up here at 20 meters per second. And if you're moving to the left here at 20 meters per second, you are also moving to the right here at 20 meters per second. There is always a cancellation. Even if you're going diagonal, there is going to be the opposite diagonal on the other side. So the average velocity of something going in a circle is actually 0. And if you do the math for it, it does come out 0. I don't want to because I think we can just see it from the picture. For every positive, there's going to be an opposite that goes with it. Do what? No, it doesn't make me cry, but it involves Pythagoras. So I'd rather not. I'd rather avoid it if I can. However, in these cases, average velocity is a bad idea. So instead of using average velocity, we want to use instantaneous velocity for these. So if you're like at this particular point between A and B, and you say, hey, how fast am I going then? If I'm on the way to B, you'd say, oh, you're going 20 meters per second. You would use the instantaneous velocity. You wouldn't use the average velocity. Same thing is if you're at a particular point on a circle, you're going to use the instantaneous velocity. You're not going to use the average velocity. Because if you pick the average one, it's just going to come out to be 0, and that's not going to be fun. Okay? Actually, it'd be really fun for y'all because then you just get the answer is 0, and then that's it. Be like, oh, 0, we're done here. Move along. Okay? Um, everybody okay so far? Y'all get the difference between instantaneous and average velocity? You understand that it's distance over time? Okay. Now for the fun part. This is the one that I'm going to have to talk about the most because this is the one that's going to hurt the most. And this is acceleration. You probably talked about it a little bit in physical science, but I'm a lot more nitpicky about acceleration than physical science people. But I mean, you're ninth graders in physical science normally, so I mean, you're a little bit older now. You can probably handle this information a little bit better. Um, by basic definition, it's either speeding up or slowing down. Remember, I don't use the word deceleration. So if we talk about acceleration, it is speeding up or it is slowing down. And the basic way to calculate it is going to be acceleration is equal to the change in velocity, change in v over the change in t. Oops. What I normally write it is a equals v over t. Okay, but this formula is a little bit limited because you don't have any information about where you started. So in acceleration equals velocity over time, if you can use it and get away with it, that's perfectly fine. But there are lots of different pieces of information about an object, like its position, for example, and delta v over delta t, or just velocity over time, doesn't give us any information about where the object started or where the object actually ended. Okay, so what we're going to have to do is we're going to have to use this acceleration to find out some different variables that could also be used as well. So v over t is the basic way to calculate an acceleration, and it's very very plug and chuggy. So if you know the velocity and you know the time, you can easily calculate the acceleration of an object. Unit-wise, the velocity is in meters per second, and the time is also measured in seconds. So that comes out to meters per second squared. Okay. On Earth, so gravity is a good example of acceleration. Yeah, so we always have a constant acceleration on us of negative 9.8 meters per second squared. In AP Physics, you can use negative 10 and be okay. So I'm going to write here approximately. If you don't know that, approximately kind of looks like an equal sign that got kicked a couple of times. Um, that's what approximately looks like. It's like a little squiggly equal sign. So in AP Physics and on the AP Physics exam, you can use negative 10 in your calculations, and it makes things so much easier and quicker. I would highly recommend you do that. Okay, so they're not going to give you an open response question that you're going to miss based on decimals. Okay, if they're going to give you an open response question, you can easily use negative 10 for gravity. You don't have to remember the 9.8. If you want to get specific, and in labs that we do, the 9.8 is probably going to be what you want to use. But in a pinch, negative 10 will get you where you need to go. Okay, now that means, and it's always negative because it goes down, right? What if you're in Australia? Yeah, gravity always points towards the center, right? It all depends on that reference point because whenever we start our reference point, like we are at a specific place on the earth, so we say down is that way. But if you're in Australia and you're literally upside down, whenever you point down, you're pointing that way, and that way is negative to them, okay? But it doesn't matter because it feels normal, okay? Australia puts their maps upside down? Do they really? Are you being serious to me? Or really? That's kind of funny. I like that. I did not know that. I had no idea. But yeah, that would be really funny to be in there and like go into history class and look at the world map and it's upside down and be like, "Yo, bro, what are you what are you doing?" Uh, the hurricanes, the toilets, ah, the toilets. Yeah, hurricanes do the same thing, so they'll rotate the other direction. Um, okay, so do we want an example of a problem with acceleration, or we're good? Yes? Okay. All right, so let's say that we have an object. Now, since this is v over t, we have to be careful with our velocity and our time. I can't give you any problems that have position in it, but we can actually try to calculate the position if we're clever enough. And that's what I'm probably going to save that for tomorrow, though. I'm not going to do that right now. Um, so if we have an acceleration, then let's say that we have an object and it'll look like, I don't know, a marble. And it's originally has a velocity of 20 meters per second, and the velocity then goes to 60 meters per second. And then amount of time, so if we were to actually, I don't want to put a space there. I'll just write t equals 4 seconds. Okay? All we have to do is just calculate our change in velocity and our change in time. So the acceleration is equal to 60 meters per second, because the change you do final minus initial. So the final one is 60, the initial one is 20, and then that's over 4 seconds. It's like I did this on purpose for you guys. 60 minus 20 is 40 meters per second, and then divide by 4 seconds, and that comes out to be 10 meters per second squared. Not too bad. If you start off, the same thing can happen and you can get a negative acceleration. So if we take the exact same situation, but the object is going slower, two positive velocities can end up with a negative acceleration. So if you have the marble and the marble is actually slowing down instead of speeding up, then let's say that this one starts off at 30 meters per second and this one slows down to 10 meters per second. By the way, the arrows, these are vector quantities, which means they have a magnitude, they have an intensity, and they have a direction. So whenever you guys are sketching these, try to make your arrows have the magnitudes that are appropriate. It doesn't have to be to scale because I don't care that much, but 30 needs to be a larger arrow than 10. It doesn't have to be a whole lot bigger, and you don't have to like worry about it being 3 times bigger, but at least show me that the arrow is larger on one side than the other one, okay? Because that'll kind of help you guys conceptualize what's going on. If we calculate the acceleration, that's going to be delta V over delta T. So that's going to be 10 meters per second minus 30 meters per second over, oh, I didn't give us a time, did I? How about 4 again? Let's just do T equals 4. Divided by 4. So 10 minus 30 is negative 20 meters per second, and then divided by 4, which would be negative, was that 5? Said it right, yeah. Negative 5 meters per second squared. So if you have two positive velocities, it can very much equal a negative acceleration. And that's kind of what I was talking about yesterday. If you are slowing down, it's because you have a positive velocity and a negative acceleration. So this thing is slowing down because it's going from 30 to 10. Our velocity is positive, our acceleration is negative. That's going to cause a slowdown. If both of these speeds were, if we were going from like, say, um, the top one, 20 to 60, so we have a positive acceleration and we have a positive velocity, so that means that the object is actually speeding up. The signs match up. Okay? Another good way to remember that is by this chart. So velocity, acceleration. If you have a positive velocity and a positive acceleration, or a negative velocity and a negative acceleration, these are speed up. If you have a flippy flip, then these are slow down. Okay? Some people like the table to help them out. And I think pretty much with those positives and negatives, that if you look at those 4 situations, all that covers like all of your situations. Like if you can think of another one, let me know. If you have a, so um, 0 can go both ways. It's like I was actually saying, can anybody actually come up with another one? But like if you have a 0 velocity, 0 could go both ways. You have to think about which way it's actually going. Okay, so if you have a 0 velocity, um, there is usually no acceleration that goes along with it. Okay, because it's not moving. Fair. Um, but you can have something that has a zero instantaneous velocity and still have an acceleration happening to it. So that is something that we kind of have to be careful about. Um, Questions so far? Are we all okay? Let's see here. How much time do I have left? I only have 4 minutes. Oh my gosh, time flies when we're having fun. Let's see here. Dang. That doesn't really bother y'all, does it? Okay. Um, I'm going to, because there are 3 assignments that I'm going to give you guys with, oh no, I lied. There's only 2. Like position and velocity and acceleration. I'm going to give both of these to you guys, and it's not really that bad. Some of this stuff is things that you've seen before. Let me see if I can actually zoom in and get to it. There we go. So like if I were to give you like a position and a time, you could actually graph both of the positions and the time on a graph. When you do this, and anytime we're actually graphing stuff out, make sure that time is always on the x-axis. If you ever have time, it is always on the x-axis. Okay? And then anything that you want to put here can go on the y-axis. This is not limited to position. We could put velocity there. We could also put acceleration there because any of those things are time dependent and they can change with time. So we can put any one of those things on there and it actually make a realistic graph. The horizontal thing is called the what variable? Uh, okay, there's horizontal and vertical, but in science we call them. That's math. In math, we call them the x-axis and the y-axis. Independent and dependent variable. Okay, the one on the bottom, this is the independent variable. Okay, and the one on the top is the dependent variable. Dependent. Because one depends on the other. Okay, and it doesn't work backwards. Like for example, um, if as time goes on, you can move from one position to another. But it doesn't work backwards. If I go back to that position, it doesn't mean that time went backwards. Okay? So position depends on time. Time does not depend on position. So we always want to put the time as the independent axis. We do not want to put it as the dependent axis because what that implies to us, and this is just a standard that everybody uses. If you put time on the y-axis, it doesn't make it a wrong graph. It just makes it a confusing graph because we always in science put the thing that is independent on the x-axis and the thing that is dependent on the y-axis so we can see how things change over time. Okay? Does that make sense? A lot of times that does that as well too. The stock market is the same way. Like if you put because time goes here and either the index or the price goes up on the y-axis, if you flipped it over, it would mean that as the price goes up, time goes up, and as the price goes down, time goes backwards. And it doesn't really make any sense. Okay? So that's why we do that. It's just to make sure that we don't get confused. It's a standard that we used a long time ago, and we just stick with it. So the independent always goes on the X, and the dependent always goes on the Y. Any questions? Okay, I'm gonna unlock both of these for you guys in Canvas. You don't have to do it tonight. If you want to save it for the weekend, you're more than welcome to, because I'm not gonna ask you about these things tomorrow. Tomorrow, I'm gonna pummel you guys. If we're here, I'm gonna pummel you guys about kinematic equations. And if you're not here, I'm going to make a video and say a lot of crap. Okay? I'm going to. Oh, there we go.